I'll jump right into my overview and tell you what I'm going to talk about. So I'm talking about, it's a fairly new concept that we call Tracially complete C-star algebras. And it seems like an interesting new thing, and I wanted to kind of share a lot of the questions around it. So it's new, and it has origins that are not as new, but also somewhat recent. In Tracial ultrapowers and really originating in work of Matui and Sato. There's a powerful kind of framework that has led to proving a lot of things, which I'll go over. And it's a field that has a lot of open questions, which I'll get to at the end of my talk. So the plan for my talk, I'm going to talk about Tracial ultrapowers, their use and their structure in the classification of C-star algebras. And then I'll get from this to what we call tracial completions of C-star algebras, and then tracially complete C-star algebras, the main object of my talk. I'll talk about a property gamma and some results coming from this, and then I'll have questions, and then maybe you'll have questions. I mean, I liked how Henry stopped a lot to ask for questions, so I'll try to do that too. Or if I don't do that, or you have a question, please just turn on your mic, interrupt me. I'm happy to take questions like that, as long as 50 of you don't do that at the same time. Okay, so actually there's some interesting connections between, well, maybe not connections, but Matt's talked a lot about Choquet theory, and we'll see a bit of that in my talk as well, though from a somewhat different perspective. So for me, I tend to... Sorry, okay, I don't think that was a question. I think that was some background noise. I tend to forget the proper definition of a Choquet simplex, and for me, the definition of a Choquet simplex is it's the trace space of a C-star algebra. So I come from this from a different perspective, but we'll see some commonalities in the things that I talk about. Okay, so I'm going to talk about tracial ultrapowers. So we're going to start with a C-star algebra, and throughout we'll use T of A to denote the set of traces, by which I mean tracial states. And for all of this, we want finite C-star algebras, and on top of that, we want C-star algebras that have traces. So we assume pretty much throughout that the trace space of the C-star algebras we're dealing with is going to be non-empty. We define what we call the uniform 2 semi-norm on the C-star algebra as follows here. So the 2U semi-norm of A is the supremum over all traces of the trace of A star A, and then you take the square root of that. So you might recognize kind of if you did this with just one trace, you get what's commonly called the 2 norm associated to that trace. Comes up in the GNS representation, that sort of thing. So this is just doing the same thing, but you take the supremum over all traces, and that's the uniform bit. Okay, now from this, if you also take a free ultrafilter, then you can define what we call the tracial ultrapower, or I've often called it the uniform tracial ultrapower of A, as the following. So you take bounded sequences in A, and then you mod out by sequences for which this 2U semi-norm converges to 0 along the ultrafilter. Okay, so that's as a theme. If I put something in blue, it's just repeating it from the previous slide. So, okay, so in the unique trace case, let's say we have a C-star algebra with just one trace, we'll call it tau. Then we can take the GNS representation associated to this trace, completed as a von Neumann algebra. And then it's a fact that this, if you take the von Neumann algebraic, the tracial ultrapower, then that's right. Okay, there's a typo here. I guess I wrote 2u in here, which should have just been a 2. But so this thing I've written down. I mean, I guess you could write 2u, but either way, you get kind of a classical von Neumann algebra construction. It's known that this will be a von Neumann algebra, in fact, a 2-1 factor, and by the Kaplinsky density theorem, you can see without too much effort that this new thing I defined, this tracial ultrapowers, is the same as this m omega. So some simple conclusions we draw from this is, first of all, that this tracial ultrapower, at least in this case, is a very tractable object. It's a von Neumann algebra, and we all know that von Neumann algebras are much easier than C-star algebras. And also, it also forgets a lot about A, right? I mean, if A, the C-star or the von Neumann algebra you get by taking this GNS representation is really going to forget all sorts of fine structure about A, and then we're doing that, and then we're also doing this further thing of taking the von Neumann algebraic ultrapower of that. So we lose a lot of information about A when we do this. Okay, so just by comparison, I'm not going to talk much about this, but there's a much more common ultrapower used in C-star algebra theory, which is the norm ultrapower. It looks very similar in definition. The only difference is this thing we're modding out by sequences which converge to 0 in just the usual norm for the norm ultrapower, and for this tracial ultrapower, we do things that converge to 0 in this other 2u norm. Okay, but there's a bit of a buzzword. So there's a relationship between this 2u norm and the regular norm. You can show that, which way is it? The 2u norm is going to be bounded above by the regular norm. So it follows that this tracial ultrapower is a quotient of the usual ultrapower, and the kernel of this is something that is discussed often in the results I'm going to talk about soon, called the trace kernel ideal. I'm not going to talk more about it, but if you've seen that, you know, it fits into this whole picture. Okay, so the origins and kind of the applications of this tracial ultrapower go back to some work of Matui and Sato on the Thomson-Wiener conjecture. So this theorem here was a big breakthrough published in 2012. And the breakthrough is not only the strength of the theorem, but also the new ideas that went into it, which I'll talk about. So it says if you have a simple nuclear C-star algebra with unique trace, and it has strict comparison of positive elements, then it is Z stable. Okay, I'm not going to go into the strict comparison, what that means. If you've seen it, good. If not, it's this theorem is a part of the Thomson-Wiener conjecture, just to give some buzzwords around that. And Z stability, I'm also not going to go into that, but it's so what they did here was they proved one of the implications of the Thomson-Wiener conjecture in this restricted case of unique trace. Okay, so I'll say a bit about how they did this. Okay, the fact that we had unique trace, as we saw before, this tracial ultrapower is a von Neumann algebra in this case. So it gives very powerful structural properties of A omega, and that really, in a sense, the key property that they needed is property gamma, which we'll come back to later. And then so that gives us these things about A upper omega, but remember, is this tracial ultrapower A upper omega forgets a lot of things about A. So other things are needed to bring it back to get a property of A. So A being Z stable is a much finer property that you don't see just by looking at this in this case some GNS representation of A. So they had this other property, this property SI, which was used to relate properties of a commutant of A in this tracial ultrapower to the commutant of A in the norm ultrapower, and once you get to the norm ultrapower, then it's much closer to proving things about A. Okay, so that's a summary of kind of the idea, very high level idea behind their proof. But they with this they kind of set a framework of to prove things about C-star algebras, which is as follows. So 2 steps. First, you establish structural properties of A, of the tracial ultrapower, A upper omega. And this, I mean, in the case where you have unique trace, this happens kind of for free. For other cases where there was kind of more sophisticated things that came later. And the second step is you use some extra information to transfer these results to the norm ultrapower, where it's much closer to proving things about A. Okay, and this framework, it's been used many times, so I'm just going to run through a whole list of results which use this framework. And I mean, you know, each of these steps can be embellished a fair bit, and so I'm not going to suggest that these results are all necessarily easy, but they all kind of have this idea, this flavor to them in the arguments. So first of all, the Matui and Sato results assumed unique trace, and then this was generalized to the case that that the trace space has a compact and finite dimensional extreme boundary. So compact extreme boundary is this condition that it's a Bauer simplex that Matt was talking about. But then on top of that, we need the extreme boundary again. We need to say that it's finite dimensional. This slide's packed as it is, so I couldn't list out all the names of the people. At the end of my slides, I've got a bibliography where I expand all these. So, and I'll just say them out loud. So here, there were three separate teams who all proved this independently. The first, well, I shouldn't say first. They're just listed in some random order. There's Kirchberg and Rudam, Sato, and then Toms, White, and Vinta, who all did this. And I'll point out that Kirchberg and Rudam really made some further systematic developments to this idea of the understanding of the tracial ultrapower and its relation to the norm ultrapower. Okay, 2 more results here. So if you have a simple unital nuclear quasi-diagonal C-star algebra with unique trace, which is Z-stable, then it has finite decomposition rank. That was done by Matui and Sato. And then if A is simple, nuclear, and Z-stable, then it has finite nuclear dimension. This was done here. These are not independent, but this is kind of each team kind of generalizes the previous one. So the first was Sato, White, Vinta, and then Bosa, Brown, Sato, me, White, Vinta, and then there was Castellanos, Evington, me, White, Vinta, and then so we up to there it was kind of the unital case of this, and then Castellanos and Evington did the non-unital case as well. So this has been fully established now. So this represents one implication of the Toms-Vinta conjecture proven in full generality. And then there's some other things, some things by Chris Schaffhauser. So he did a new proof that every faithful trace on a nuclear C-star algebra is quasi-diagonal. So some quasi-diagonality theorem. And I have to say it's a very nice proof, and it does use in different ways in kind of these previous applications, but still this kind of framework of you use properties of the tracial ultrapower, and then you use more information to get properties of the norm ultrapower. Okay, and then Chris also proved that every exact UCT C-star algebra with a faithful trace embeds into, well, I said an AF algebra, really a simple unital AF algebra. Very striking result, which he did fairly recently. And then building on this, there's some work in progress, a new proof of classification of appropriate C-star algebras, simple, nuclear, UCT, separable C-star algebras. So Chris has a bit of an air of mysticism around his talk, with the title, I think, not being up there yet. But from what I've heard, I think he's going to say more about this in his talk. Okay, so those are some applications. Those are reasons that this has really come to seem like an interesting thing to look at, this tracial ultrapower. So I'm gonna move on now to getting to tracial completions. So where do these fit in? Back when we started, I said that in the case where you have unique trace, we can describe this tracial ultrapower in terms of the GNS representation of associated to this trace. And beyond the case of unique trace, there's this thing, the tracial completion, which I'm about to introduce, which replaces this GNS representation and plays exactly the same role. And the way we define it actually is a way you could view, you could define sort of the GNS representation. It's maybe not the, I mean, it really depends on having traces, but it's going to be kind of, it shouldn't be too unclear that this is a generalization of this. Okay, so I'm going to here, we're going to have a C-star algebra, and we're going to have a non-empty subset of the traces, and we're going to define something a bit more general than the 2U norm, right? So if X is the whole trace space, then what I'm defining here is the 2U norm that we talked about earlier. But now, for various reasons, we want to define this beyond that case. Okay, and then we define the tracial completion with respect to the set X to be the C-star algebra that we form by, first of all, this thing is sorry, maybe I called it a norm a minute ago. It's a priori, it's only a semi-norm, and I mean, if X doesn't sort of isn't faithful, then it is only going to be a semi-norm. So we mod out by things that would go to zero under this to turn it into a norm. That's a standard procedure. And then we also complete it in the sense of adding the limit points of all bounded and 2x Cauchy sequences. Okay, and you do that in the usual way. You got to do it, and you can write down what we really mean. We want to make that compatible. If two sequences should converge to the same thing, then we're only going to add 1 point for them. We're not going to add 2 different points. But technical details, a fairly standard kind of idea of doing this sort of completion. Okay, and that's what we call the tracial completion. And as I said, generally the case of interest is where X is the whole set T of A. Okay, as I said, this 2 T of A norm is exactly the same as the 2U norm. Okay, in the case that we have a unique trace, then you're just adding limit points of all 2 Cauchy sequences. So you're basically taking the completion in the strong operator topology. So you get the GNS representation. Okay, and in general, just as this tracial ultrapower A omega is an appropriate ultrapower of the GNS representation in the unique trace case, in this general case, this A omega is some object that only depends on this tracial completion. And there's nothing too deep going on here. It's kind of, you take this A omega, you look at it for long enough, and you see, this is the right thing you want to define in order to make this work. This is the right kind of object, intermediate object between A and this tracial ultrapower. Okay, so now what I really want to discuss is this new thing, what we call a tracially complete C-star algebra. So here we take a tracially complete C-star algebra is actually, I mean, the name suggests it's just one thing, but really it's a pair. M is going to be the C-star algebra, and X is, so M is, it has to be unital also. X is a non-empty, closed, convex subset of the trace space, and the fact that it's tracially complete is simply the property that M is equal to what you would get when you take this completion, this tracial completion with respect to X. Okay, the case of interest is what we call factorial, and that's where X is not just any closed convex subset, but a face. Okay, so that's the definition. I'll just say about this condition 3. Condition 3 is a succinct way of really saying two things. So when we take this completion, we did two things. We turned this 2x semi-norm into a norm, and we also added all these, we completed it. So it says both of these things are true, that it's already a norm and it already contains the limit of all these Cauchy sequences. Let's do some examples. The first example is what you get from the tracial completion we have before, where you let T of A, or you let the set X be kind of the set of all of T of A. So we're taking here the completion with respect to the set of all traces, and here I wrote T of A again. I mean, T of A is really a set of traces on A, but all of these traces extend by continuity to traces on this potentially bigger object, this completion. So it becomes a subset of traces on this completion of A, and one can show that it is going to be closed and it's going to be a face. And this is right. To do this, we just need to know that the trace space that we start out with is non-empty and compact. So, for example, if A is unital and has traces, then it'll be non-empty and compact. There's something slightly non-trivial. If you look at the definition here, the first thing in this pair has to be a unital C-star algebra. If you start in this example with A not being unital, this tells you in particular, when you take this completion, you're automatically going to get a unit. And this comes down to T of A being compact. That forces that. Okay. Another example, if you take a von Neumann algebra and it has a faithful trace, then you can let M be this von Neumann algebra, and you just take a singleton set, and that'll be a tracially complete C-star algebra. We don't care much about that in general, but when M is a factor, which means it has unique trace, then it becomes a factorial tracially complete C-star algebra. And this, I believe, is where factorial comes from, although I didn't come up with this. Co-authors came up with this name, so I'm just guessing a bit here.
That is the reason.
Thanks, Chris. All right. Okay, some other examples. This next example is called a trivial W-star bundle. I'm not really going to say what a W-star bundle is, but it's a nice example. I think it gives a lot of intuition to what these objects really are. they're an interesting mix of measure theory and topology in a way, and this example really demonstrates that. So here we're gonna we start with a finite factor with trace tau n, and we also start with a compact Hausdorff space, and we define C sigma xn to be the set of all bounded functions from x to n, which are continuous in the 2 norm coming from this trace. So they're not norm continuous; they're continuous in this sort of von Neumann algebraic sense. Okay. Now, if you take the set of probability measures on x, you can identify that with traces on C of x, and in a canonical way, this sits inside the traces on this set C sigma xn. So I've written down the formula here, but it's just you've got a function, this 2 continuous function from x to n, and you just at every point in x, you can evaluate that and then take the trace using tau n, this trace on n at each point, and then you just you use that and use this probability measure to give you a number by integrating over x. Okay, and this thing is a factorial tracially complete C-star algebra. So this is, as I say, this is it's a mix of measure theory and topology in a sense. So, if we took just usual continuous functions from x to n using the operator norm topology on n, then for example, where any projection in there is going to have constant trace or constant rank. But when we do it this way, you can have projections in here with their trace varying as you go along the space x, and so you get kind of interesting things in here. And as we'll see towards the end of my talk, when I have questions, there's a lot of open questions even for this example, which looks fairly concrete. Okay, so there's this buzzword W star bundles. I'm still not going to define them, but you might have heard of them. Is this idea introduced by Ozawa, and rather than define them, I'm going to tell you some facts about the case, the Bauer case. So we have mx being a factorial tracially complete C-star algebra, and we're going to assume that the extreme boundary, which I wrote with boundary with sub e here, indicates that is compact and closed. So in Matt's talk, we call these Bauer simplices. So in that case, we get a lot of extra structure. So first of all, we get a canonical copy of the continuous functions on this extreme boundary sitting inside the center of M. And along with that, there's a canonical conditional expectation going from n to this copy of continuous functions on the boundary. And on top of that, this conditional expectation recovers our special norm, our 2x norm. So the norm of A with respect to 2x is just you take the conditional expectation to this central continuous functions on the boundary, and you just take the sup norm of the result there. Okay, so this theorem, as I've put it as a theorem, I mean, really, Ozawa's notion of a W star bundle is something with kind of these properties. Okay, so I'm going to give another example, which we call the toy example. When we were working with these tracial completions and stuff, there was a period of time before we really understood how to work with the Bauer case, where we had Ozawa's theory of W star bundles, and we had the theorem on the last slide, and then the general case. And this toy example was kind of something that we used to to test certain hypotheses and ideas. This example, I won't say it solved any big problems, but it's something to get started if you want to kind of go beyond this case where the extreme boundary is compact. So first we're just gonna fix an isomorphism between 2 by 2 matrices over the hyperfinite 2n factor, which I'm denoting by R as per, so 2 by 2 matrices over R and R. Okay, and we'll define M to be the set of all sequences, all bounded sequences of things in the hyperfinite 2n factor, such that the sequence, when you go out in the sequence, it's going to converge in the 2 norm to this diagonal matrix that has the first 2 elements on the diagonal. And so that's a 2 by 2 matrix over R, and we collapse that. We identify that with something in R. Okay, and then X is going to be the closed convex hull of a bunch of traces, and these traces are as follows. Tau I is just, so we've got the sequence. You just take the ith element of the sequence, and you take the trace of that. Okay, so this thing, one can show that this is a factorial tracially complete C-star algebra, and here the extreme boundary is not compact. This is sort of in a sense, sort of a minimal example where you have this. So here, I mean, how do we see it's not compact? Well, the extreme points are just going to be these traces, tau 1, tau 2, and so on. Okay, but if you go out along this sequence, because the ANs have to converge in 2 norm to this diagonal thing involving the first 2, the traces are going to have to converge to the average of the first 2 traces. Okay, and that average, right there, we're taking a convex combination, so we're not in the boundary anymore. We're at some other place in the set X. Okay, other examples. So Matt talked about this Poulsen simplex, this mysterious showcase simplex in which the extreme boundary is dense. Okay, we know how to construct something, a factorial tracially complete C-star algebra that has this Poulsen simplex as the set X. And I mean, one way to do that is you can construct an AF algebra where its trace space is X and then take its tracial completion. But this object, it seems in a fundamental way, is going to be much harder to understand or write down in a nice way than like the toy example or these W star bundles. So I mean, is there a nicer way of viewing this object? That's a very vague question, but a bit of an interesting question, I think. Okay, so I wanted to talk about property gamma. Okay, so when we have a tracially complete C-star algebra, we can do a version of a tracial ultrapower. Okay, and then we say that the tracially complete C-star algebra has property gamma if there's a projection in this ultrapower which is central, so it commutes with M. M sits in a canonical way as kind of constant sequences in this ultrapower. And the projection, oh, big typo here. I said that the trace of the projection is 1, but actually it should say the trace of the projection is 1/2. And that should hold over all traces on this ultrapower. Okay, so in the unique trace case, really this MX is just a 2n factor and the X is the unique trace on it. And in that case, we get Dix-Me's characterization of property gamma for 2n factors. Some of the other examples, if we have a finite factor, then and we take this trivial W star bundle construction, this is going to have property gamma exactly when the factor we started with, n, has property gamma as a von Neumann algebra. And another example, if you take this tracial completion of a a C-star algebra, then one condition that would imply that you have property gamma is that A is Z stable. This is the converse of this is by far not true, but this is kind of, it's useful to know, and this is often the situation where we know that this thing has property gamma. Okay, it turns out to be a very powerful hypothesis. So we have this theorem that's been building up and festering and accumulating authors. So let's see if I can get these all in the right order. We have Carrion, Castellanos, Evington, Gabe, Schaffhauser, me. I think I put in 2 W's as sort of force of habit. There should only be 1 W there. White. Okay, and it's a classification of certain tracially complete C-star algebras. So it says, let's say you have 2 of these factorial tracially complete C-star algebras, and I say separable. We need to interpret that in terms of this 2x norm that you have on these things. We assume that they have property gamma, and also assume some sort of amenability, which here is I'm going to say is just that every tracial GNS representation is hyperfinite. Okay, when we have that, then as long as x and y are isomorphic as simplices, so affine homeomorphism between them, then they are isomorphic as these richer structures, these tracially complete C-star algebras. Okay, a corollary of this is that if we have a separable nuclear Z-stable C-star algebra, so the Z stability gives us the property gamma and the nuclearity gives us this hyperfinite condition, then the completion we get from that is approximately finite dimensional. Or another way of saying that is it's isomorphic to a completion of an approximately finite dimensional C-star algebra. Okay. This result is a generalization of the case where of the Bauer case, which is due to Ozawa, and there he does it more explicitly and shows that you get a trivial W-star bundle automatically. Okay, so I'm going to end my talk with some questions. There's a lot of questions, a lot that's not known about these. So throughout, it's when we define these factorial tracially complete C-star algebras and work with them, we always have to have this set X kicking along, and actually we don't really know if that's necessary or not. So we don't know if there's an example of a factorial tracially complete C-star algebra where X is not just equal to the set of all traces on M. We also don't know, kind of in a lot of specific examples, whether this is the case. So the case really of interest is where we take the tracial completion of, say, a separable nuclear C-star algebra. We don't know in that case. These very concrete, intractable looking things, these trivial W-star bundles, we don't know if it's true in that case, or sort of the most trivial of these. So you just take, so I said this trivial W-star bundle where X is the 1-point compactification of the natural numbers. Even in this case, this one, maybe it's a bit embarrassing, but we don't know the answer here. Okay. Another question. In this result, when I talked about property gamma, I also mentioned this sort of amenability hypothesis that we need to get a classification of these. So if we take something that satisfies this amenability hypothesis, do we automatically get property gamma? We don't know that, and again, we don't know this even for some special cases. In this case, if we knew that we got property gamma for free, then this would resolve the last piece of the Thomson-Vinick conjecture. Okay, we also don't know this in the case of W star bundles or where the extreme boundary is compact. However, Ozawa did, when he was working on these W star bundles, he did show that the answer is yes if we assume the extreme boundary is compact and also finite dimensional. Okay. There's some norm regularity questions. I'm going to breeze through these because I think I'm out of time. So these things, they look a lot like von Neumann algebras in some ways, but we don't know if they have sort of von Neumann algebraic property that we might expect, like real rank 0, stable rank 1, and comparison of projections. And we don't know these even for these kinds of cases that should be easy, interesting, that I discussed before. Okay, some last questions. Okay, let's just ignore this question. I meant to change this a bit. But the last question, is there a tracially complete C-star algebra such that its ultrapower doesn't have comparison of projections? This one, I think, is an interesting research project. But I'll stop here. Thank you very much for your attention. And I'd be happy to take any questions.